opponent， 然后我们是阿元 AY13， 我是吕书贤 Susan， 陈仁硕 Ted， 周国伟 Wesley， 黄国浩 Lawrence 跟吴家豪 Eric。
我是 Team 2， 还是高雄女中，然后我是杨佑英，他是很喜欢吃，他是陈佑琪，然后他是陈佑琪，他是好危险。
那按照惯例，评审也要跟各位同学自我介绍一下。那就是我是杨佳慧，我来自逢甲大学，然后请这边评审的顺序自我介绍就可以了。
我是招聘者，我来自师大。各位评审、各位大家好，我叫王伟华，我来自中研院。
大家好，我是洪振勇，我来自北京大学。
大家好，我是薛亚维，从中央大学。
那按照这个如果各位同学没有什么状况的话，那我们就现在就当现在就开始进入比赛的那个模式哈。那当然就是说，如果没记错的话，要开始做所谓的这个选择题目。So let's begin the problem selection. So I think the procedure should be the opponent will challenge problems, right? So.
Okay. I'll challenge jeweler trick.
We accept it. Wow. Okay. So by protocol, all your please write down the reporter's name, opponent's name, and the reviewer's name on the blackboard. Okay, and write down the problem name, the problem topics. 麻烦评审老师麻烦写一下他们的这个姓名，要在这个评审板上面写这个姓名。那个已经开始计时了。The clock is ticking, so 5 minutes for preparation, right?
You can see the time.
Can you show the whole chart?
往上。
Oh, thank you.
我有下载。他两个也下载。
我在看报纸。没有看报一开始没插吧？你知道是哪里？我应该关起来。帮我注意一下种子，这是种子跟你的什么比例？然后往前流，直接用那我这还需要开始。我看得懂。我能听到。那是新的，直接把这个对。拍到。
Now the recording may commence. You have 12 minutes. 12 minutes.
Okay, so good afternoon, honorable judges and fellow contestants. I'm YC from Fresh, and today I'll be here presenting you with problem 14 ruler trick. So let's start with our all-out. Here's our all-out, and here's the problem statements. Place a ruler on the edge of the table and throw at its rear end. The ruler will fall. However, if you cover part of the ruler with a piece of paper and repeat the throw, then the ruler will remain on the table while the ball will bounce off. Explain this phenomenon and investigate the relevant parameters. And here's our main focus. So we will be discussing the relation between the length of the ruler out of the table and the max force it can withstand, and the relation between the width of the ruler and the max force it can withstand. And so here's our demonstration video. So you can see if there is no paper covering on the ruler, the ruler will fold. And if you cover it with a piece of paper, the ruler stays still. And so our guess is the air pressure does the man force that allows the ruler to stay on the table. So we do our experiment in the vacuum system. So as you can see, so it's a vacuum system, so there's no air pressure. So the ruler will still fall down. And so to further prove that air pressure difference does take main role in the whole system, so we do our experiment on a surface which is full of holes, and which means that the air will come in, just come from those holes, which will create no air pressure difference. So as you can see, the ruler will fold. So here comes our theory. So this is how we define our ruler. So you can see the little L is for the length, and the X is for, as I mentioned, the the lens outside of the table, and R is for the rest of the lens, and the W is for the width. And so in the case, the ruler we use in our experiments, the thickness we didn't take into consideration because the thickness is really small, so it wouldn't affect a lot on our experiment. So, and you can see from the ball drops here, okay, so drops here, and there will be a force created by the ball, right, the drop in. So there will be, so here's the pivot point, so I didn't, oh yeah, this is the pivot, so there will be a torque F created, and which is the length X cross for F0. And so for how we define F0 is the rate of change of momentum per time times sine theta. So the point of we times sine theta here is to ensure the contact angle, like the contact angle the ball drops here, do be in the consideration. But in our experiments, we suppose that theta will be 90 degrees for better calculation. And there will be another torque created by the ruler weight from here, the balance points, and the application range is from the balance point to pivot point, and which creates a torque of ruler weights. But as you can see, the ruler weight is really small. So in our experiments, we wouldn't take this torque into consideration because the value of it is really small. And so the phase 1 before collision, you can see P1, we define P1 and V1. So P1 is the lower hemisphere, which is 1 ATM, and this is the phase 2 after collision. As you can see, the ruler goes high and created V2, which is V2 strongly increased, which according to the Boyle's law, V1 is just here, right? So as V2 strongly increase, the P2 will strongly decrease, and so we can get delta P here equal P1 minus P2, and we define a coefficient in our experiment K, which is delta P over P1. And so this is the motion of collision. So this is, as I mentioned, phase 1 and phase 2. And so for as our hypothesis, there will be a force which is caused by air pressure difference that will applies on another end of the ruler that makes the ruler remain on the table. So you can calculate the torque P from this equation. And yeah, although we times sine theta here just for the contact angle, so that will be also a consideration in our experiments. And so, according to balance of torques, we can know, in order to hold the ruler on the table, so we can know that torque P equals torque F, right? And so we put it into this equation, so finally we can get a theoretical value of F, which is here. Okay. And so at the phase of collision, as I mentioned, there will be a low pressure region created here, right? So our experiment have to calculate the exact value here. So we divide the value of it. So we into a triangular prism and a tetrahedron here, and so we can get our V2 value here, and we can get the other we can get another P value afterwards, and go on. And so here's our experiment setup. We got 2 bones here and around the ruler and the drops here, and we place ruler here to be a to specify the length here, so we can put it into tracker, so we can measure the length at the V2 value, so we can get finally V2 here. And this is our equipment. So we use newspaper as people use, and the ruler, as I mentioned, is acrylic, and so the weight and the thickness is so small, and we got different lengths, different widths of it, and it will be in our experiments. So if our experiment 1 is about the independent variable is the length outside of the table, and so to emphasize our control variable here will be the collision mode. Like the point is we drop this it's always a bowl, like the problem statement, and so we can get the charts. So from if you put if the more lengths outside if there's more lengths outside the table, the jumping heights will decrease like this, and we can get the height, right? So we can get into this equation and we can get the f, the experiment value of f, and we put it into comparison. So as you can see, this is how we get from our experiments, and this is the theoretical value as I mentioned in my theory. Okay. So here comes the discussion. So you might be wondering why this gap did decrease after, you know, the trend goes down, the gap between goes down, right? So it's because the length, you know, when there's just only 2 centimeters outside of it, there will be a lot of, you know, there will be like 13 rest of it inside underneath the paper, which when you are throwing the ball, it will create a larger area for the air to come in. So the arrow will be bigger. Okay, so here comes our experiment 2. So we redo the sand independent variable, but this time we use a force sensor to do our experiments. And as you can see, this is how a force sensor works. You can record the force you drag on it and tell you the exact force you drag. And so here's the trend we get the chart, and we put it into comparison with the theoretical number here. And you can find out, so the discussion of experiment 1 and 2, you can find out if you do it in, like if you drop it with a ball, it will be an exponential relation. And if you do it with a force sensor, it will be an inverse relationship. And it's because of because if you drop it with a ball, the contact time will increase as this, which affects the accuracy of the calculation. And go on, the third experiment is about the width of the ruler. So the others are all the same circle and all. So as you can see, we do different widths of the ruler, and you can see from this trend, it goes down. If the width increase, the force you can withstand will like going up like this and keep going. Like you can see with different widths here. Yeah, still different widths here. Okay, so our first experiment is about. So it's also an independent variable is also the length of the ruler outside the table. So we are calculating the minimum air pressure. So go on. So as you can see, if there is more length outside the table, we need more air pressure. This should be value here from 0 to 0.9 over here. So as you can see, we need more pressure difference as the length of the ruler outside of the table. And this is because the delta P here. And so discussion is for, as I mentioned, we define the K here. So throughout the experiments, the K wouldn't really affect, like if we change the length, it wouldn't affect. But so because it's related to the air pressure, right? So as experiment 4, we change the value of the air pressure. So it do changes and strongly. And so here comes our calculation. So our final calculation is that the length sticking out of the table is negatively correlated with the force that the ruler can withstand, and in the contrary, the width of the ruler is positively correlated with the force that can withstand. Thank you. This is my presentation.
Go ahead.
There are some questions I want to ask. How can you define your V1?
So basically, can we go back to there? So V1 here is like the thickness of the ruler, right? So it's really small. We do not take into consideration like it's a really small value, so it wouldn't affect a lot. So we did not just that's not a big trouble.
If the V1 is very small, and how can you find the if you didn't measure the V1, how can you answer how can you say the P2 times by V2?
So basically, as I mentioned, we do have V1. So V1 is about, as I mentioned, the width times the whole volume of the ruler, like the width times the height and the length of it. We do have that. We didn't show that because, like, we do calculate it. We do got V1. So basically, because it's calculatable, so we do not show it off. So
and you say mass will the air will flow in, right?
yeah, right.
So how can you use the PV is a constant?
A PV.
P1
So I mean the air flowing. So this caused the increase of the value, right? So that would still be a constant, like, because that like P2 is like, yeah, sorry, wait. So that's a constant.
Okay, time's up. So now the preparation for the opponent, 3 minutes.
翻看特口，但是我可以攻击的点。
决热过程到3度。温正的数据，然后缺点是但数据量也是很大。要说PV relation。他刚好讲到这个问题，就是那个Newton's law of relating。therefore rotating。然后第三个那个 how can you control the height？ 然后 the L dot how can you take a calculation of F dot the F点零？你直接打 F 点来选项。对，剩下这种讲。那个 summary。这边。
Hands up. So So the opponent, please, your time is starting.
Okay. Okay. Okay, this is our summary of the report. This is the problem statement again, and okay. The summary is the report did their experiment in vacuum system at first to ignore the resistance and prove the phenomenon is related to the air pressure. Then they focus on the length of the ruler out of the table and the width of the ruler. Okay, these are some pros and cons. First, for pros, they consider the not air resistance is the pressure differences, and second, their data is quite enough. And the cons are they only did 2 parameters, and they just use the balance of the torque, not tau equal to I alpha. Third, they didn't consider the thickness and the weight of the ruler. Okay. Alright, let's go into our discussion.
Okay. So the reporter, please stand by.
Hey, first, I want to ask the PV relation. Why did you use the PV is a constant?
So basically, the ruler is a constant, like static. So the value of the ruler is the same, right? And P1, as I mentioned, is a normal atmosphere, which is 1 atm. So in this case, these two times together will be a constant number. So we can get it on to B2 times P2.
Okay, then why did you use the PV is a constant, not PV to the power of gamma is a constant. This is the we also did you agree with the period or the time of the phenomenon is very short, right?
Yeah.
Yeah. So I think the temperature will change inside because as the T is very small, there's no time for heat to transport. So to the first law of thermodynamics, du equal to dq minus d. I think this is close to 0. So when the volume under the paper and the ruler increase, I think the internal energy of the air will decrease. So I think the temperature will decrease. So how do you think about that?
So you're saying the change of the temperature will affect these two values?
Right. So I think this is better than the PV to a constant.
Can I? So what's your point about? Like, can you tell me about how does the temperature differences affect those values?
No, you use the PV is equal to a constant is PV equal to constant. It's from the T is a constant, right?
Oh, yeah.
Right, but now T is not constant. What do you think about it?
Right. So what we do, in our experiments, we do it in our experiment environment is like we got like constant temperature like below. Because there wouldn't be so much like temperature difference because our lab is fully with air conditioning. So we ignore this in our experiments. So because in the environments we do with our experiments, this wouldn't be such a big affection.
Can I see your data?
Okay, sure. Which page?
Is there any page about the max force?
Max force.
Max force.
Here, this one.
No, with theory. With theory.
With theory?
With theory. Yeah, with theory.
Go.
That's page. Right. Right. This.
This one.
The theory presents the I'll think about it. And next, we want to talk about how do you control the height of the bulb dropping.
You mean in what? So do you mean this? Do you mean this one?
Right.
No, we do not control. Like, it is a independent variable for us. So, we drop from different heights.
Use hand, right?
No, we do use hand, but we got measurements. Like we got a equipment which can measure the exact value of height. So we drop. So the height is really appropriate.
But I think your hand can cause error. Did you consider it?
So this is the reason why we got error bar here. So this will affect it.
Okay. Thanks. And I want to ask about your balance of torque.
Okay.
Right. You just use the balance of torque, but do you think the torque cannot be balanced if the ruler rotates, right? In the process, the ruler will have a small change of the will rotate a little bit.
Sorry. So do you mean about something like it might fall, or you think there will be another torque created?
If you think your ruler as a ring body like this, you did the experiment by measuring the height changing by time of the ball, right? And okay, good. But if you can measure the height of the ball, that means the ruler is related, right?
Sorry, related to what?
Rotated. Sorry. Rotated.
Yeah, the ruler do rotate.
So the torque shouldn't be balanced, right?
No, I mean, so for the first, the torque F is when the hits, right? But the torque P applies on when it reach the angle, like it goes like this, right? And
right.
This is a moment that the torque of the pressure it applies on. So there will only be two torques. So in order to balance that, in order to keep that static on the table, so we assume that will be torque balance.
But I think the torque should not be balanced out as your ruler is rotated, because rotated require a net torque. This is the force caused by the aircraft, right? And it's the and this is the force the ruler receives from the ball, right? If the net torque the ruler receives is 0, and according to the Newton's mechanics of rotating, the alpha the
I see your point. So you do see here we times sine theta here just to show the thing that you mentioned. So I think in this point.
sorry.
I think in this point. So I think we can just discuss this by changing the sine theta value. So it could differ because we do not get the exact angle of that, so we just assume as a whatever context. Like if you mention this one, so yeah. So this is why the reason why we put sine theta there, so to show there might be some error on the things you mentioned.
Sorry, I'm not asking about this. It's about when the ruler is rotated, it should receive that slope. So if the ruler of mass is not much smaller than bow, you should consider the moment of inertia of the ruler. Did you agree with that?
I think that could be into further extreme, so that would be that could be taken into consideration. Maybe we can do further experiment on this one.
Oh, okay. Then for the bow receive the bow act to the ruler. You didn't consider the mass of the bow, right? The mass and the gravity force of the bow, right?
You mean in torque balance or?
Right, in torque balance.
So as the segment and our experience, the balls would just the ball creates a full scale stair, right? And it immediately bounces off, so it wouldn't do a secondary context with the ruler. So we do not take that in consideration.
But so how did you measure the force and how did you figure out the force changing by time? For the bow act to the ruler.
Oh, so we use as I say, can you go back to the one this one? So this is the rate of the change of momentum here. So we define we got this. So we change this into this in order to calculate the value of torque F.
What's the small m?
M is for the mass
of the what?
of the ball, because the ball is a line.
I think it's mean the force of the mass of the ruler. I thought.
Yes.
Right. You consider your fixed point. Your fixed point. Here, right?
Yeah. Yeah.
Right. So a capital L minus x should be here, right?
Oh yes. You mean
Yes.
this one?
So I think it is for the ruler, right? Not
This one is for ruler and this one is for ball.
But you should consider gravity of the ball.
Okay.
Right.
I think the time is up. Okay, let's proceed to the next phase. So the opponent have 1 minute. It's counting now.
Okay. To summarize the discussion, and first the reversing the PV relation should be PV equal to a constant, but I didn't think so. I think the temperature should not be a constant because the time is very small, and for the Newton's law of rotating, I don't think they should use Hertz balance because the mass of the ruler shouldn't be equal. Okay, that's all. Thanks.
So now the question of the reviewer to the reporter and the opponent and answer to the questions. Okay? So the reviewer, please be ready. You have 3 minutes. It's counting.
How do you think about the error between theory and experiment in experimental work?
So going into the first, please. Next one. Next one. You mean this one? So you mean why does the error, the gap between this theory increase, right? Decrease. So it's because as you, this is a 2 centimeter outside of zero, so which means there will be more length than this one inside on the ball, like it's like this and this. So if you got more length inside the table, right? So it will open up more spaces for the air flowing, which cause the gap between them.
How do you think about it?
I'll just think about the gap, right? I thought if there's a problem in theory, it's you cannot simply saying the gap is just caused by the air flowing into. It's probable that it's caused by the problem of theory.
Okay, so what does it change massively between 2 centimeter and 3 centimeter?
As again, 2 and 3. The 3 centimeter ball. What does the gap change? Or what? What does the gap change? The max force. I don't really know because I didn't agree with the theory, so I can.
So you mean why does the gap between here goes down to like this? So as I mentioned, inside the air, the volume of the air, and the amount of the air flowing in, so created like this, and there will be some, there will be some error in. So this is the reason why we define the coefficient K here. So basically, this is the one that, this is the one that caused all the gap between here and all the errors. So because we cannot do that to really precise, so there will still be some, some differences. But just as it goes, the trend goes down, the gap and the error will get less.
Just 1 centimeter, there are errors too.
So yeah.
Okay. Sorry, I have to cut it short. It's time's up. So the preparation for the reviewer will have you have 2 minutes. Then the reviewer will have 4 minutes for her presentation. Reviewer, please take the floor, and it's counting.
Okay, so I'm talking about the problem number 14 relationship. And the reporter's pros and cons is the reporter theory is very clear and he understands the problem well. And he has the deep discussion in it. But it's too nervous and the variable is not enough, it's just then. And the pros and cons to opponents is he understands the problem and quick question. He has deep discussion with the reporter, but the cons is the quick question is too slow. And don't think much about the theory, which is, I think the reporter doesn't understand the statement well. He don't have this one. He happens to. And the discussion to opponent with reporter is, he asked consider air resistance, and the reporter answered that P1 times B1 equal to P2 times B2. And the next question is, he doesn't consider the mass of a ball, but the reporter say just apply the force. So you don't need to consider the mass of the ball. And the opponent also asked, didn't consider the moment of inertia. And the reporter say he just improved in further experiments. And I asked the reporter and opponent, how did they think about the error between theory and experiment in experiment 1? The reporter just answered that the error is because the length of the ruler. But this question. And the reporter also said angle is a cause that make error between theory and experiment. But this question, I don't have time to ask them, so thank you.
So now the conclusions from the reporter. You have 2 minutes.
So as the opponent and the reviewer mentioned about the air resistance, I would like to emphasize that I use a vacuum system is because I want to prove that the pressure differences it says on the ruler, which is the main forces that lead to the equilibrium. So it's not about air resistance. And about an opponent raised the problem about thickness. So as I mentioned in the earlier beginning, the thickness, the glue we used, the thickness is really small, so we didn't take into consideration. And so for PV, for the PV1 constant, which is related to where your PV equals to annuity in our theory. And so the opponent was emphasizing the T might change this, but through our experiments, because the environments we do our experiment wouldn't take a lot. So I think that would be a further concern that we can do in our further experiments. And for the reviewer for opponent and reviewer saying that there should be more variable should be concerned. So we do a lot of like a lot of variables because but in the end we found out it doesn't do a lot of like they could in amongst those variables we cannot get a really good relation between related to the experiment. So we only shows up the two measures that really affects the laws in our demonstration. So maybe we can try more variable in our future experiments, and maybe we can discover something more like those tools. Okay, thanks.
So now all juries here, we would like to put exam question to those students receiving. Anyone? Please stand by.
We go to page 23. So you got the theory values from this formula. You got the red dots from this equation. From this one.
So you mean about theoretical value?
Yeah.
So you're saying where does this come from?
No, I'm saying okay. So you have the red dots.
Red dots.
The theory values, theoretical values.
This.
Yeah. And so you need to know the value of k and also sin theta. So how do you get those values?
Oh, so as I mentioned, so in our experiments, we discovered like when we are doing the throws, we found the angle, the theta angle is nearly to 90. So for easier calculation and for easy calculation, we define theta to 90 as I mentioned in my presentation. And k is a coefficient that we define. So k is delta p over p1. So k times p1 is equal to delta p here. So yeah.
So you cannot define k because you need to plot those red dots, right? So you need to know the values. Okay. How do you get the value?
W k, and it's just a constant that we find. It's not.
No, let's go back to 23. So even though it's theory, but you still need some numerical values to plot those red dots.
So you were saying like.
Do you have some values to show?
So there should be more database of this?
Yeah.
Okay, so maybe that could be in our further experience.
All right. Any other question from our jurors? Please.
I have a question for opponent. So, why do you think the temperature has to be considered as a variable?
Right. When we calculate the sound speed, we not use the process of equal temperature. I don't know, but is that the energy isn't transferred by heat. So it's should you P V gamma is a constant because the process is very fast. So I don't think the T is a constant.
You're considering some heat transfer in this scenario.
I don't think that in this collision there's enough time for heat transfer.
Okay, so the temperature should be constant. Okay, thank you. I have one question for the reporter. So you look at the page 2 in the very beginning. Next. the theory one.
The theory one.
Yeah. Next one. Yeah. So this the first equation, how the right top is the force times the position, right? So why? Because and x is the length that extends to the over the table, right?
Yeah, this one.
Yeah, but your ball it doesn't force on the edge of the ruler, right?
Sorry for I missed that. But in our experiments, we control this, but dropping balls because we got a lot of data masses, so we choose the one that we managed to make the collision points at the end of that one. So maybe there will be a little bit gap here, but it will be really small because we try to make it on the very edge of it.
So you only choose those data when you hit the edge.
Yeah, so because we do a lot of science.
But you need to say, because your figure doesn't show that.
Yeah, the figure is kind of.
You should plot at the edge.
Oh, okay, sorry.
Because this one, right, the position is not as small.
Yeah, I see.
Yeah, and usually it's correct. Okay, thank you.
Okay, thank you very much. I think the time is up. So now that we have please our juror here try to calculate the score here. And just take your time. Don't be hurried. So I think everyone has all the jurors have finished their review. So okay, I will show all the jurors please show the score for the reporter. Okay. Let me write it down. 5, 5, 7, 5, 6. Okay. So now we ready to show the score for the opponent. Sorry. 4, 6, 6, 5, 5. Okay. So now the score for the reviewer. 4, 5, 5. 5 and 4. Okay. So now we conclude the first part of our competition.